In this video, we provide an introduction to solubility equilibria. Alright, in prior videos, we have looked at acid-base equilibria, and now we're moving forward to try to understand a different type of equilibrium which involves solids. Okay, so think about a solid substance, an ionic solid, that is going to be AB. Alright, so there's a couple of things that can happen here. This solid can be at equilibrium with its ions, okay, which are going to be we're going to call them plus in aqueous, and then B minus, which is in aqueous phase. So if this is a soluble salt, a highly soluble salt like sodium chloride, what will happen is that this equilibrium will be fully displaced to the right. Okay, and again, that's the case for many soluble salts like any sodium salts or any nitrates and so forth. The body of our discussion is going to concentrate on salts that are sparingly soluble. So this will still be ionic solids, but what happens is that this equilibrium is displaced towards the left. Okay, so for example, think about calcium carbonate, which is a solid, very prevalent on Earth, right? Exoskeletons of insects are made by calcium carbonate. Eggshells have quite a bit of calcium carbonate, and obviously when you put calcium carbonate in water, it looks like not much dissolves. In reality, there's a little bit of that dissolves, so it is true that you actually have some concentration of calcium 2 ions and carbonate, calcium ions and carbonate in solution. Okay, but it turns out that the equilibrium constant for this process would be very, very small. Right, so let's try to see how we would write the equilibrium constant for this process. Okay, this K would be simply the activity of products multiplied or to the power of the stoichiometric coefficients divided over the activity of reagents, right? So carbonate, 2 minus, and then the activity of calcium carbonate. Here all of the stoichiometric coefficients are 1, so we don't have to worry about the powers. Now when we map these activities into useful measures of concentration, what we find is that, well, this is a solid, so the activity is 1 by definition, and then we're only going to have terms left in the numerator. Under that case, we can say that, well, here we're going to have the concentration of calcium ions divided over the reference concentration, multiplied times the concentration of carbonate, divided over the reference concentration, and generally we just simply drop these reference concentrations and yes, write this as calcium multiplied by the concentration of carbonate ions. Okay, but notice that what these reference states do is just cancel the units so that that equilibrium constant is dimensionless. Right, so this equilibrium constant that governs how a solid dissolves into the ions is called the solubility product. Okay, so we're going to call it KSP. And again, the value indicates how soluble the salt is. So for calcium carbonate, this solubility product is very, very small. Okay, so the value is 2.8 10 to the minus 9, which gives you an indication for the very small amount of calcium and carbonate ions that you have in solution. There are other examples where the solubility products are even smaller. For example, we can take the case of bismuth sulfide, this salt, which is a solid, right? The equilibrium will be 2 bismuth ions, 3 plus, which are in aqueous solution, plus 3 sulfide ions. Right, so when we come to right here what the solubility product would be, this KSP would be the activity of bismuth to the squared, and then the activity of sulfide cubed over the activity of the solid, but of course that's going to be 1. So then once we divide by reference states, this is going to be equal to the concentration of bismuth 3 plus squared multiplied by the concentration of sulfide 2 minus to the power of 3, and the value for this equilibrium constant, this solubility product, is very, very small. This is just 1.1 10 to the minus 73. Alright, so that very large negative exponent tells you that this salt barely dissolves. Okay, so in the next few videos then we're going to see how we can use the solubility product to learn things about these sparingly soluble salts, or what we call insoluble salts, and then what type of problems we can do with them.